Hello, so this is the chapter review on chapter 12, and we will go over only the first part of chapter 12. And so chapter 12 is on chemical bonding. And before we start, I want to show you that there is a document that is necessary when you are dealing with chapter 12. So let's show you here when you are in the home page of the Canvas course, and you are looking at the chapter 12 module. There is the electronegativity and molecular geometry document. And so I want you to have this document open when we go over this chapter review. This will be a necessary document, and it will be available when you have an exam that comprise chapter 12. So it's there in the chapter 12 module. So let's start the review with question 1. The relative ability of an atom in a molecule to attract electrons to itself is called the atoms, and here it's missing a word, and the word is electronegativity. The atom's electronegativity is the ability to attract electrons to itself, and that's a very important property. And the document you will find in Canvas, and let me show that document, not this one, this one. This is the document I was showing you in Canvas, and it shows you a table of electronegativity values. And so these numbers, it goes basically from 0.7 to 4.0. Francium on the lower left corner has the lowest value, and then fluorine with 4.0 as the highest value. Notice how the noble gases are not included here. So that's where you will go when you need those values. So question 2, what is the difference in terms of electrons between an ionic bond and a covalent bond? So let's remind you that if you haven't not learned that yet, you need to remember that ionic bonds are between metals and non-metals. Remember how metals are on the left side of the periodic table and non-metals are on the right side of the staircase, in the periodic table. And covalent bonds are between non-metals or between non-metals and metalloids. And so the difference between these two types of bond is that an ionic bond is when electrons are transferred from the metal to the non-metal. So there is a complete transfer. The electron is gone from the metal, and now it's the non-metal that has it. And that's typical of an ionic bond, because then the metal will become a cation and the non-metal will become an anion. And that's how they are attracted. A covalent bond is when non-metals are sharing electrons to gain an octet of valence electrons. An octet of valence electrons means 8 valence electrons. And so non-metals, they don't like to, give away their electron, and they prefer to actually gain electrons. But because when you put two non-metals together, they, neither of them is willing to give the electron to the other. So then they share electrons instead. So that's what's the difference between an ionic bond and a covalent bond. Next, what is the difference between a non-polar covalent bond and a polar covalent bond? So, okay, this only happens between non-metals, right? Because it's covalent bonds. And some bonds, covalent bonds are polar and others are non-polar. And it's all depending on the electronegativity difference between the non-metals. So you're using the table of electronegativities, calculate the electronegativity difference between the two bonded non-metals. And if the electronegativity difference is large, then the atom with the most electronegativity will attract the electrons closer to him or itself, much more than the other atom, and so that will create an unequal sharing of the electrons, right? The nonmetals will not share equally their electrons, and that leads to polar bonds. If the two nonmetals are having similar electronegativity, then the electronegativity difference will be close to 0, and then the electrons are shared equally between the two nonmetals, and we call these nonpolar bonds. Let me show you the table here in this document. Below the electronegativity values, there is this table that you will use to classify bonds according to the electronegativity difference between the two bonded atoms. And you see that if the electronegativity difference is less than 0.5, the bond is nonpolar. Between 0.5 and 1.9, it's a polar covalent bond. And then if the electronegativity difference is much larger than 1.9, then it's considered an ionic bond. So that's the difference between polar and nonpolar covalent bonds. So now we have a list of bonds here. And for each of these following bonds, we want to determine the type of bond by calculating the electronegativity difference. And if you determine that it's covalent, say if it's polar or nonpolar. And if it's polar, you will indicate the direction of the dipole, because polar bonds have what we call a dipole, and it's represented with this arrow with a plus on one end and an arrow on the other end. And we will show you how we know how to position that. So let's start with silicon and sulfur, SiS, when silicon is bonded to sulfur. So we will need to go to the electronegativity table, find the value of silicon and then the one for sulfur. Silicon is 1.8, sulfur is 2.5. So you always do the larger value minus the smaller value. So 2.5 minus 1.8 is going to be equal to, let me make sure I don't do a wrong value here. 1.8 is 0.7. So then if we look at the table, 0.7 is between 0.5 and 1.9, and that's considered a polar covalent bond. So, polar covalent bond. Okay, so let's do CS-Cl. CS is cesium, Cl is chlorine. Cesium here in the left side of the table has a value of 0.7 in electronegativity. Chlorine on the right side has a value of 3.0. So we will do 3.0 minus 0.7. And that's 2.3, right? So 2.3 is a large value, and that's greater than 1.9. So it's considered an ionic bond. And you can verify that it is indeed an ionic bond just looking at the atoms. You know, cesium is definitely on the left side of the periodic table. That's a metal. Chlorine is on the right side of the periodic table. That's a non-metal. And so we expect an ionic bond between these two. So that fits. Silicon and phosphorus. So we know silicon has a value of 1.8. Phosphorus is just right next to it. It's 2.1. So 2.1 minus 1.8. 2.1 minus 1.8. And that's a difference of 0.3. 0.3 is a small value. It's below 0.5. So that's considered a non-polar covalent bond. So non-polar covalent bond. And, these two are, non-metals, so we expect a covalent bond between them. Oh, by the way, I forgot to add the arrow because we had a polar bond here, polar covalent bond, and it said to indicate the direction of the dipole when you have a polar covalent bond. So I need to put an arrow here above silicon and sulfur in the correct direction. The arrow should point towards the most electronegative element. And here between the two, the most electronegative was sulfur with 2.5. So the arrow should point towards sulfur. So I will have it like this. So you place the arrow above the bond with the positive end, if you will, above silicon, because that's the one with the lower value of electronegativity. And then sulfur has a higher value, it's 2.5, so the arrow points towards sulfur, like the arrow showing you the direction that the electrons are attracted to, right? They are attracted more by sulfur than silicon, and it creates this polarity with the, delta plus on the silicon side and delta minus on the sulfur side. So let's go back here to PbO. Pb is lead, O is oxygen. So Pb on the right side here of the periodic table has a value of 1.9. Oxygen has a value of 3.5. So we will do 3.5 minus 1.9. So 3.5 minus 1.9. And that's a difference of 1.6. That's a large value, and that's below 1.9, so it's considered polar covalent. So that's a polar covalent bond. So here, because lead is in the, let's look at the periodic table here. Lead is there, and then oxygen here. So oxygen is a non-metal, lead is a metal, and you would expect an ionic bond between them. But they are quite close in the periodic table, so the difference, according to the document here, says it's polar covalent. But if we were not looking at the electronegativity difference, we would have classified this as an ionic bond, right? I want you to be aware that, this way of classifying, works very well. Sometimes here without this table, we would have classified this as an ionic bond because we have a metal and a non-metal. Still here it's polar, so we will use the arrow. And the most electronegative element here is oxygen. So you want the arrow to point towards oxygen, like this. Next, nitrogen and chlorine. Nitrogen and chlorine. So chlorine has a value of 3.0. Nitrogen is also 3.0. You see they are both in the upper right corner here of the periodic table. So then you do 3.0 minus 3.0, and that's 0. So because it's 0, we know it's a nonpolar covalent bond. Sometimes we also call them pure covalent bond. Pure because pure covalent because none of the atom here is attracting the electrons more than the other. So the electrons are really equally shared. So that's why we say it's a pure covalent bond or a nonpolar covalent bond. SR and F. SR is strontium. F is fluorine. Fluorine has a value of 4.0. It's in the upper right corner there. And then strontium on the left side, next to rubidium, it's 1.0. So we will do 4.0 minus 1.0. 4.0 minus 1.0, and that's 3.0. And the difference of 3.0 is large, and that's greater than 1.9. So that's considered an ionic bond, which makes sense because fluorine is a nonmetal and strontium is a metal. So that's a polar, sorry, we said ionic bond, because we have a metal, strontium, and a non-metal, fluorine. And fluorine is the most electronegative element of all the periodic table. And then hydrogen and oxygen. This one you will see a lot, OH. Hydrogen here, notice how it is, by itself here on the top. It's a value of 2.1. Oxygen is 3.5. So we will do 3.5 minus 2.1. 3.5 minus 2.1, that's a difference of 1.4. 1.4 is considered a polar covalent bond. It's between 0.5 and 1.9. So polar covalent bond. And so because it's polar covalent, we should show which way are the electrons attracted. And the most electronegative element of the two is oxygen. So then the arrow should point towards oxygen. And then hydrogen has the plus side of the arrow because it is partially positively charged due to the fact that the oxygen is attracting all the electrons towards itself. So that answers question 4. Let's go over question 5. Consider the ions. Sc is scandium, scandium 3+, chlorine minus, potassium plus, calcium 2+, and sulfur 2-. So, and we, by the way, we call the chloride ion here, and that's the sulfide ion. So what is the total number of electrons that each ion possesses? So we'll do them one by one. So let's look at scandium. For this, to know the number of electrons, we need to know the atomic number. And we need the periodic table. Scandium, atomic number 21. So 21 is the atomic number, but then it's a 3+ ion, which means you have 3 protons in excess. So you need to remove 3 from the 21 to get the number of electrons, because scandium will have lost 3 electrons to be scandium 3+. So 21 minus 3 is 18. So scandium 3+ has 18 electrons by losing 3 electrons from the neutral atom. Next, we have chlorine. Chlorine, atomic number 17. Chlorine likes to gain 1 more electron to be like argon and have 18 electrons. So chlorine will gain 1 electron, and then from 17 has then 18 electrons. So the chloride ion has 18. After that, we have potassium. Potassium, atomic number 19. It likes to lose 1 electron to be like argon. And so from 18, you lose an electron, and that's going to be 18 as well. So potassium has also 18 electrons by losing 1 electron. Next, we have calcium 2+. So calcium 2+. Calcium, atomic number 20. When it loses 2 electrons to become calcium 2+. So from 20, it goes to 18. So again, calcium 2+ has 18 electrons by losing 2 electrons and to be like an argon. And then finally, the sulfide ion. Sulfur here, atomic number 16, likes to gain 2 electrons. And so again, it will have 18 electrons, like argon. So notice how they all have 18 electrons, right? And it's either by gaining electrons or by losing electrons. They all like to become those ions. These are what we call predictable ions, which means from the position in the periodic table, you know that they will always make this kind of ion. You know, sulfur will be the sulfide 2-, calcium the calcium 2+, etc. So the next question is, write their electron configuration. Let's bring it here. So they all have 18 electrons, right? And when you write the electron configuration, you use that number. And so if we use the periodic table to do this, first we go from hydrogen to helium, we have 2 electrons there. Here, so 2, sorry, not 2, it's 1s2. Sorry, 2 electrons in the 1s orbital. Then 2 electrons in the 2s orbital, so 2s2. That's 4 electrons in total. Then from boron to neon, 6 more electrons, and that's the 2p6. At that point, we have 10 electrons, right? 2 in the 1s plus 2 in the 2s, that's 4, plus 6 in the 2p, that's 10. We continue across sodium and magnesium, and that's 3s2. That's 12 electrons in total. And then we will go all the way to argon here to get 12 plus 6 more from the 3p6. And that's 18. So if we write this, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. And you see from the superscript here, we have, up to that point, 10 electrons plus 2, 12, plus 6, 18. So they all have this electron configuration, and it makes sense. They all have the same number of electrons. So then the question is to name the noble gas that has the same electron configuration as each of these ions. And you have guessed already, that's argon, right? Because argon is the noble gas with the atomic number 18. And so you see how they are all around argon and trying to be like argon and have 18 electrons. So that makes sense. So let's look at the next question. We need to match these ions to the following pictures that represent their relative size. Okay, I will show the whole thing before I show the drawings here. Okay. So we have these blue spheres that represent the size of the ions, and you have to match the ion to the correct size or relative size. And so because all these ions have 18 electrons, the number of electrons doesn't matter here, right? It's not what will determine their size because they have the same number. The difference in size will be due to the number of protons. The more protons there is in the nucleus, the more electrons are pulled towards the nucleus, because remember, protons are positively charged, electrons are negatively charged, so they are attracted. And the more there is protons in the nucleus, and the stronger the attraction is. And so then it pulls the electrons inward towards the nucleus when you have more protons in the nucleus. And so then the smaller the atom is. So the way to classify, give the correct ion to the correct size is by using the atomic number, because the atomic number represents the number of protons. So the smaller atom, the smaller, atomic size, smaller ion in size will be the one with the most protons, and that's going to be scandium, because scandium has an atomic number of 21. So 21 protons, 18 electrons, so they are really tightly held together. And then calcium will be slightly bigger with 20 protons. And then potassium, slightly bigger with 19 protons. From there, you go to chlorine or the chloride ion with 17 protons and 18 electrons. And then the sulfide with 16 protons and 18 electrons. So that's how you determine the relative size of these ions. Another consideration is that cations are always smaller than the neutral atom, and anions are always bigger than the neutral atom, which is why here the anions are bigger than the cations. If you look at the position of all these ions in the periodic table, here let's highlight scandium as well. So you know that normally the size decreases from left to right, in a period. And then, it increases going down. But here, scandium will be the smaller of the ions, scandium 3+, then calcium, then potassium, then you would have argon, and then chloride and sulfide. So that's the number of protons here that matters. So next question, question 6. Why are valence electrons of an atom the only electrons likely to be involved in bonding to other atoms? So what are valence electrons first? Valence electrons are the electrons that occupy the valence shell. And the valence shell is the outermost shell of the atoms, right? The outside one. And so when atoms are bonding, their valence shell will overlap. So, to kind of draw this, imagine two circles and you bring them closer together until they overlap, on one side. And so that's what happens. The shells, overlaps, except that it's in 3D, right? 3-dimensional. And so they overlap. And in that zone where they overlap, that's where the valence electron will be shared between two nonmetals, for example. And because it's only the outermost shell that overlap, that's why it's the valence electrons that are shared between the two nonmetals. In ionic bonding, it is also the valence electrons that are lost or gained, because that's the one that are the most accessible. So they will be lost more easily, also because they are farther from the nucleus, right? They are held less tightly by the nucleus. So they will be easier to pluck out of metal, and then they will move into the valence shell of the nonmetal. So that's why valence electrons are the most important electrons. That's what determines the properties of all atoms, actually. This is the most single, thing that is the most important in bonding. Question 7, what is an octet? Why do atoms follow the octet rule when bonding? So you will learn in chapter 12 how to do Lewis structures. And so all atoms, when they are bonding, they follow the octet rule. So what is an octet? We said that earlier. An octet is 8 valence electrons, right? Octet comes from the root octo, which is the prefix for 8. So an octet is, 8 of something. And here in chemistry, it's usually for 8 valence electrons that we use this term. And so all atoms try to reach an octet of valence electrons in their valence shell. And so they typically don't have enough. And so they will either gain electrons to get an octet or lose electrons to, reach the octet of the previous shell. Or they share electrons to have 8 around them. That's what nonmetals do. And why do they do that? Why 8? It's because it's a very stable configuration. It is the electron configuration of noble gases. Notice how noble gases here in the periodic table are in group 8A, which means they have 8 valence electrons, except helium. So neon, argon, krypton, xenon, radon, and oganesson, they all have 8 valence electrons, and all other atoms try to be like them. All other atoms try to be like the noble gases, as far as the electrons are concerned, right? It's only about electrons. Because noble gases are very stable, very unreactive atoms. And in chemistry, we say that they are inert. It's the term to say that they are very stable, they will not react, and so they can just be there on their own and be happy. And so everybody wants to be like them. So that's why we have this octet rule. But there is also a duet rule, if you will. And which atoms follow the duet rule? So the exception, there are some exceptions. A duet means 2 valence electrons. 2 valence electrons. And that's because if you look at the periodic table, helium there is an exception. It has only 2 electrons, 2 protons, 2 electrons, because the atomic number is 2 there. And so the atoms that are around it, around helium, they try to be like helium because that's the closest noble gas to them. And so hydrogen, so if we look at the periodic table, hydrogen will like to gain only 1 electron to be like helium. Lithium and beryllium, they will like to lose their valence electrons to be like helium as well and have 2 electrons in their valence shell. So then hydrogen, lithium, and beryllium only need duets to be like helium, the noble gas that has 2 electrons only. And please remember, helium is an exception among the noble gases.